Hello. What I'd like to show you now is what the derivative is in calculus. Now, let's go to this whiteboard. Y equals f of x and y equals x. Now, the limit, we have 2 points here. We're trying to find the slope, okay, of a line at this point. The line tangent to the curve f of x, okay? So we know that the slope m, we usually call it m in algebra, is change in y. So that's a bad looking delta, okay? Change in y divided by change in x, okay? Rise over run. Change in y, if we have a slope, let's say of a line, we have change in y, okay, over change in x, okay? Here's your change in y, your rise, okay? Delta y, which is going to be what they call rise, over the change in x, which is run. Okay? Now, but what about the slope of a curve? A curve, if we have a curved line like this, curved line, instead of a straight one, slope's changing at every point. How do you find the slope? Where do we find the slope? Suppose we want to find the slope here. I can't draw a straight line, do rise over run, okay, because it's going somewhere else. Second point's not on the line. What we're looking for is a slope at a point tangent to the curve of the line, that it touches just at one point. Now, if you look at this diagram here, diagram on the right, okay, sorry about this. You have these lines with 2 points in the line, okay? We call these secant lines. Not the tangent line here, but a point from the function to another point on the function, okay? We can call these, let's say, y1, sorry, x1, and here is y1, and we'll call this point x naught, y naught. Now, what is the rise is change in y? Rise is this. Change in x, delta x, is just change in x. Run, Okay? Now let's look at these points here. And this is also going to be M. Now let's move x1 closer to x. Let's make the new x1 here. Now here's the secant line. Let's keep moving x1 closer. Keep moving x1 closer to x naught. You notice these secant lines come closer and closer to the tangent line. Well, when x1 equals x naught, that's a problem because you're dividing by 0, even though y1 will also be the same as y naught, because you can't divide by 0. So we can take the limit of y1 minus y naught over x1 minus x naught as x naught goes to 0. Okay? Now, let's write this in a way where it's easier. We know that y is the same as f of x. So this is going to be f of x1 minus f of x naught all over x1 minus x naught as the limit as x naught goes to or sorry, x naught doesn't go to x1. x1 minus x naught here goes to 0. Sorry about that. x1 minus x naught goes to 0. Or x1 minus x naught approaches 0. As the limits, we take the limit as x1 minus x naught approaches 0. Okay? x1 is getting closer and closer to x naught. Okay? That means f of x1 is getting closer and closer to f of x naught. You're still divided by 0. We get arbitrarily close. Infinitesimal distance. Okay? Now, x1 minus x naught is delta x. Okay? And then delta x1 is x naught plus delta x. So we have f of x naught plus delta x minus f of x naught all over delta x and we take the limit now as delta x approaches 0. Okay? So now we're here. Let's get another whiteboard. Okay? So we have this. Can I replace this x naught with just any general x? Can I replace the x naught with just any general x? Well, here's how this happens. First, x has to be on the domain of the function, okay? X has to be part of the domain. Any x on the domain. The first requirement is that it has to be continuous. Suppose I have a function like this. This function is a jump discontinuity, okay? At this point, x naught. So even though it's on the domain, it's not continuous. And besides being continuous, x must be differentiable, okay? So if I have something like this, let's draw a blue function, okay? If the function, call this blue function g of x. Now at this point here, g of x is not continuous. Okay, at this point, we'll call this point x naught. This point x naught, g of x is not continuous. Okay, the function's not smooth. That means it's not differentiable. If you notice here, that means there's no slope. Okay, if there's no slope and a sharp corner of a function, that's what it is in the Cartesian graph. Not differentiable. Now, but if we can assume that if the function is, let's say, continuous and differentiable everywhere, okay, or even just at the point we care about, if we have a continuous differentiable function, we can just place x naught with any general x, okay? So let's do this. I'm going to draw Cartesian plane. Here. Familiar y and familiar x. Now, and again, we have the formula for the derivative, okay? F of x plus delta x minus f of x all over delta x. Sorry about this bad writing. And then we take the limit as delta x approaches 0. I'm going to choose a function. F of x is x squared. I'm going to find the slope of this curve at x is, let's say, 1, 2, 3. Maybe x, let's make this here, point here. Let's make this point here, x equal 3. Now, I can go up here. So you find this point here, okay? This is where y is, okay? And then we can draw the slope of our tangent line here. This is kind of crude. Let's make it a different color. Green this time, okay? So let's draw the slope of our tangent line right here. Draw our tangent line right about. Okay. That's kind of crude, but it's supposed to be this line that touches one point. And this is f of x equals x squared. Okay. And so we want to find the slope. So we'll start with this. F of this is going to be 3. I'm going to make this easier, just a bit easier. And this is common to what textbooks use. I'm going to make delta x equal h. So it's easier to write. Okay, 3 plus h squared minus 3 squared all over h. Okay, we have to take the limit as h approaches 0. So this is a binomial, 3 squared, which is 9, plus 2 times 3 times h, which is 6h, plus h squared minus 9 all over h. Notice the 9's go away here. We're left with 6h plus h squared all over h. These two h's cancel out. So we have 6 plus h squared over h is just h. Now we take the limit as h approaches 0. This h just goes away. We're left with 6. Okay? So the slope of the line, f of x is x squared, is 6 when x is 3. And that makes sense. So you're going up on the x squared curve. You're going to have a pretty steep slope. So let's look for the general formula for f of x is x squared. Okay? So let's look at this. Okay? You've got of x is x squared. Well, let's say we want to find the general formula for the slope of the tangent line for f of x is x squared for any x. Okay? And we don't have any issues with the domain. Like I was showing you earlier, f of x equals x squared is continuous for the whole domain that goes from negative infinity to infinity. So here's what we have. We have f of x plus h, where h is delta x, minus f of x all over h. And now we can, but this is going to be, we put in specific values, we use x plus h squared minus x squared all over h. And now we have x squared, multiplying this out, x squared plus 2hx plus h squared minus x squared all over h. Okay, these x squareds go away. Okay, we can factor out an h from the numerator. H is good times 2x plus h all over h. And we can do this. So now we take the limit as h approaches 0. And that just, we make h 0 and we get 2x. That function is the derivative of x squared, which we sometimes say f prime x. Okay? We sometimes write as f prime x or df over dx. Okay? That tells you the slope of the tangent line of x squared at any point x. And that's an introduction to the derivative. Thank you.